our screen is visible now, Roshan.
Right, sir,
Video
right,
is
sir.
Yeah, visible,
Sir,
visible.
Sir, visible. Yes, sir.
You are visible. You are alone visible.
sir, it's okay, sir. Conference also is not visible, no, sir.
No, you are
No,
visible.
conference
Background is visible. Your background behind something is there, lamp or something.
some
Nothing.
tube lights, something like.
Okay, sir. Okay, sir. Just I will correct it, sir. I think people are sitting here.
Okay.
Arnachalam sir, maybe you can try changing the camera option to HD poly this thing.
Arnachalam sir, can you request professor to give some exclusive tips for exam?
Yeah.
Because I tried yesterday, I failed.
No. Exclusive today. Please listen to the class today and tomorrow carefully.
Okay.
More carefully. That is what a tip I can give.
It is exclusive for
exclusive for your class representative on behalf of Arnasalam. So these today class carefully listen, take notes, proper notes. Every class important. So today and
Sure,
tomorrow.
Sir. Of course, sir. Thank you, sir.
Yeah. I tried to record yesterday also. In between there's a break, something like that. Some noise. Recording is not full here and there. I think I should have to record separately. When online teaching, sometimes I don't know. No issue. That is not a big issue. Shall we start the class?
Sir, 2 minutes, sir.
Yes, sir.
Yeah, we'll wait. No issue.
2 minutes.
Absolutely no issue. So there was no rain there. Hot sun.
Sir, yesterday there was a heavy rain, sir, at evening, only for 15 minutes. I think,
because
sir,
why I'm asking is there are two cyclones, one in Arabian Sea, other one Bay of Bengal. Bay of Bengal is hitting Tamil Nadu. In Arabian Sea, there they say it will be Gujarat, Maharashtra, that side. Right? There can be rain. There are two cyclones simultaneously. That's why I thought your area may be getting rain.
Yes, sir. Yesterday there was a heavy rain for 15 minutes.
Okay.
But after that, there is no sunshine only.
Okay. That is good. But rain is very important. Otherwise, drinking water, crop, farming,
Yes, sir.
everything
Yes,
is
sir.
a problem.
Sir, in Bangalore, any sea, there is a cyclone, Bangalore will get rain. So it's been raining since morning.
Oh, Bangalore also. Oh.
Yes, sir. It hasn't stopped since yesterday late night.
Oh.
So I went to office in rain. I have come back in rain.
Okay. That means same thing will be Bengal here and the same cyclone is affecting you
Basically,
also.
any of the two seas it rains, Bangalore will get rain.
That is good. Double advantage, correct?
Yeah, but unfortunately, municipality is very bad in Bengaluru. So the newer localities will get rain drenched, like it is a tier 2 city or something.
Oh. But one more thing, what I noticed is Bangalore, the city roads are very small. They cannot expand also. Because
It's not that, sir. It is very inconsistent. Like the same road in one area, it will be very wide. Suddenly, it will become as narrow as a needle. So traffic will get bottlenecked there.
Yeah. Because I was coming there frequently for 1 year. Because I was doing a project for the BEML, Bharat Earth Movers. So monthly once I'll come and stay there for 2 days. Correct. We complete the work and because I was consultant to BEML. They were doing a big project for army, and the design I have to verify vetting. Once this one before they start doing the project, the design should be verified completely, entire machine, mechanical, electrical, electronics, and hydraulics, all those things. So they given a project to me, it's IIT, this one. So I come and there stay for 2 days, 2 or 3 days monthly once for 12 months. So they do the work and show entire month whatever they're projecting to me slide by slide. Results what they achieved. I give the correction to the team will be sitting with me who are doing the work, design work. So then they modify next month, they come and show like that. So that time I saw as you are rightly correct, some places there are 4-lane, 6-lane road also inside the city, suddenly become 2-lane like a village. Absolutely, there's a chaos because one time I want to catch the airport, new airport. My flight was 6:30. I started by 4:10. I reached by 6:10. just about door was about to close. They said even 1 minute you would have missed the flight. It took to more than 2 hours, 5 minutes or 10 minutes to reach a 30-kilometer distance, something like that.
Well,
I'm
welcome
talking
to us.
more than 8 years before. Right now, I don't know. That time
I
is so
mean,
much.
pretty much the same still. It isn't better, it isn't worse.
No, because now population increasing, vehicles are increasing. No, that's why I said now it should be still be difficult to travel inside city vehicle.
It has grown unevenly, sir. So that's why you won't feel that difference. But like you won't even feel like city has grown in these areas also. So it will suddenly grow in those areas.
Oh,
So it
okay,
has
that is
grown
good.
very unevenly and it's very unplanned. So they're taking over villages and converting it
Okay.
into.
Sir, we can start, sir.
Okay. Okay, no problem. We'll discuss later. So, good evening. We were talking about sensors. That is one of the prime important component of the control. Especially wanted to control a machine. You need a feedback sensor which measures and provide the feedback so that accurately control, specifically for closed loop control. We will talk about it when we talk about what is a closed loop. Yesterday we saw about what is a transducer and the definition and the sensor and what is an actuator already we saw. Then also I introduce a term called electronic sensor because all the sensors are going to provide electrical signal. There are sensors which doesn't provide electrical, so old generation sensor like a pressure sensors. I told you yesterday, board on tube or bellows, all these things. There are many mechanical sensors that nowadays is not in use. Almost completely overtaken by electronic sensor. We talked about sensor, bidirectional sensor, regular sensors, what is loading effect, what is a smart sensor, because sensor generate a signal proportional to input parameter, can be anything. The output of sensor is generally electrical sensor, means it will produce in the millivolts, microvolts or milliamps current only. That is not sufficient, which has to be amplified. That for that we are using amplifier and filter circuit to remove noise. If everything is integrated in a single component, which is called a MEMS sensor nowadays, correct? That is called as smart sensor. Amplifier, filter, sensing element, including ADC, DAC also included. Digitizing component, that is called this one. Then we saw about different type of sensors classification. This is a classification which generally I used to tell in this course. And there is a sensor whose resistance is changing depending upon input parameter. Example, strain gauge and temperature, RTD. They work on principle based on resistance of any given wire R equal to rho L by A. This is L. And where rho is the resistivity, L is the length of the wire, A is the cross-section area. When the wire is subjected to a force, the length can tensile a compressive force, a wire, then length will reduce or increase. Simultaneously, area will increase or decrease. So if you substitute those values, change in this one with in the formula, you will get there's a change in resistance. The change in resistance is proportional to force or torque or this one. That is called a strain gauge. The other one is called to measure temperature, RTD. If you take any wire, metallic wire, it has the formula is this. At any given time, the resistance of the wire is proportional to its current temperature, which is called T naught. And then that can be, what is current resistance can be found if you know the present temperature and also the temperature called reference temperature and the reference resistance, this one. And using the formula, you can calculate. Here, the alpha is called a temperature coefficient of the wire, the RTD sensor. I told you this is generally used platinum. Platinum wire is most widely used. Otherwise, you can use copper or copper composition. These are two type of RTD sensor. Most widely uses RTD is using platinum. But please note the platinum very expensive, like gold, very expensive. If you want precision measurement accurately, then you go for RTD made of platinum. Otherwise, copper plus some composition, other material, mixed material will be used to make the RTD sensors. That we will see. That works on principle of this formula. The second type is capacitance type. Two parallel conductors separated by a dielectric constant, and dielectric media having a permittivity epsilon, and the separation distance is D. Then A is the common area between the two plates, they call capacitor. This can be used for measuring all those things we talked. Then inductive chain, RPS and LVDT, then piezoelectric effect used in piezoelectric transfer. We are going to see the sensor later. Just try to take the classification. What are different classes? 6 classifications: thermoelectric effect, photoelectric effect, piezoelectric effect, change in inductance, change in capacitance, change in resistance. These are the formula relevant to this. This formula is meant for strain gauge. This formula is meant for RTD. This is the formula for this one. This is the inductive sensor. We are going to see in this class and next class. Okay, this classification, please note down. Most important classification. As I told yesterday, if you see any sensor, wherever you're using an electronic sensor, it will fall under any one of the category. Its resistance may change, proportional input parameter. Its capacitance can change, its inductance will change, or it may generate charge based on piezoelectric effect depending upon input. That means force or pressure or torque. Then thermoelectric effect and the thermocouple is subjected to junction. It produces an EMF that is proportional to temperature input. So that is called thermoelectric or Seebeck effect. Note down, this is called a Seebeck effect. Thermocouple works on the principle of Seebeck effect. When the thermocouple junction is exposed to the temperature, then it produces EMF. The EMF is proportional to temperature. That is called Seebeck effect. Then photoelectric effect. These are sensors. Now we will see one by one. What is a capacitive sensor? Capacitive sensor, as I told you, that capacitance is nothing but two parallel plates. For example, I have two parallel plates. One plate is this black color, and you can see that it is extending up to this, but they are overlapping. For a specific purpose, I shown as overlapping. One plate is this black color plate, parallel plate, square type plate. Other one is the red color plate. Okay, we are seeing from this side view. This is side view. Okay, that means there are two plates, and basically I can say that one plate, the other plate. I say P1, this is P2, same size something. Now one plate can be fixed, it cannot move. Other plate, I say this is P1, the second can move. And what means I can move this plate like this. I can move like this. If I move that, what happens? Initially, when the two plates are separate, there's no common area. Okay. If the plates are coming together, there is a common area. For example, you can see the video, correct? My hand, you can see, correct? This is like my palm. This is one capacitor that is conducting. Capacitors are two metallic plates. My one palm is one metallic plate, same material, can be copper, aluminum, any conducting material. Other one is another plate. Both the palms are equal in size. Now, if I see from front, they are separated by a distance, correct? The distance is this D. In this formula, capacitance of a capacitor, C is nothing but capacitance, called as unit is farads. Note down, it is called farads. And the capacitance is equal to epsilon A divided by D. In this, epsilon is called as permittivity of the material. Permittivity of dielectric material between the plates. Dielectric material which separates the two plates. Okay. So for example, as I told you, I'm keeping my hand like this. Both they are separated by the distance. Now, if I keep my left hand and move my right hand, what happens? D is changing. Right? Please note that this area, and if I put like this, both the hands are aligned. In this case, this area A in this formula, A in the formula is nothing but the common area. When both hands are aligned, the common area is the width by height of my palm. Both are aligned. Now, if I move, please know the capacitor both plates should not touch. If it touches, it is not capacitor. It should be separated by non-conducting material. What is non-conducting material in between my hand? Now, air. Correct? Right now, the air is there. So, that air has a permittivity. Epsilon. That permittivity equal to 1.00015. Then, permittivity for free space. For example, I go to space, maybe 100, 400 kilometers, above 100, 200 kilometers, and I put my fan like this. In between, there's no air also. Only free space, empty space is there. Empty space also has a permittivity. That is called as free space permittivity, which is marked here. You can see that epsilon naught is nothing but dielectric constant of free space. The value is observed to be 8.85 to 10 power minus 12 farads per meter. Correct area. Correct. We are talking about this one. So then epsilon naught is a free called ER. Epsilon R represents relative permeability. So this value of E naught is taken as 1 for normalization purpose. With respect to this air, correct, in atmospheric air as 1.01, that means you have to multiply it by 8.85 into 10 power minus 12 to get the actual E of the air. E of the air, I can say that it's ER multiplied by E naught. E naught already we know. And ER is 1.0015. If I'm correct, you have to check in the book if you need it. Multiplied by 8.85 into 10 power minus 12 is the permitted air. That means in this one, as I told you, 2 hands. Now if both hands are aligned, for example, my palm area is for 15 centimeter square, correct? 10 centimeter by 5 centimeter width. So width into height equal to 15 centimeter. Now, if both hands are aligned, the common area in the formula C equal to A epsilon, it is 15 centimeter square. Now, suppose if I move this one, my right hand I'm moving away. I moved half the distance. Then what happens? That means the common area in the width wise, it is reduced by half. Instead of 5 centimeter, it becomes 2.5. Height remains same. 7.5 into 2.5, so many centimeter square is the common area. Now, if I keep it like this, I move the left hand is fixed, right hand I moved completely. Now, there's no common area because if I keep like this, distance is same, D is same, but A is 0, common area. So that means if I keep one plate, correct, the left hand is one plate, other plate is moving horizontally in X direction. Common area was maximum 15 centimeter square. Now it become half of the 7.7 centimeter. Now it become 3.5, the quarter area, common area. Now 0, A becomes 0. That means automatic capacitance. Instead of that, if I keep the plates like this, common area I am keeping constant. I just turn my hand and I'm moving. Left is keeping on the same position. Right hand I'm moving from distance. You can see the D. The distance between two plates is called a D, which is denominator in the formula. So that means if I vary the distance, the capacitance will vary. If I keep it like this, if I move my hand, one hand fixed, other hand, A is varying, common area. Common area can be maximum and I can 0 like this. Otherwise, I can move. This is x-axis. In the y-axis also, I can move like this. Keep the left hand like this. Right hand, I'm moving up and down. Again, A is reduced. Common area means the area which is covered by both hands surface. So that means if I go like this, common area becomes 0. That means if now I can use this for measuring displacement in X direction. There are 2 plates. One plate is fixed. My left hand is considered one plate. Other plate I'm moving up and down. Correct? Common area is moving. Otherwise, I move left and right, x-axis. Again, common area is moving. A will vary. That means if I vary this, the capacitance is varying. C is varying. Correct? So if I measure capacitance, I can know what is the displacement this hand plate is moving, capacitance plate. Up and down also. X-axis movement, linear movement, y-axis movement, or z-axis. Correct? One plate is fixed, other plate is moving in any direction without touching. Correct? Where this is going to be your capacitor. So this is how the capacitor can be used as a sensor. Okay. So that is what I showed. Now, if you understand that, you clear. Now, capacitance contains of 2 parallel pair, P1 and P2, and they have a area, and this is fixed. For example, P1 is fixed, P2 is moving. If I move this, now what is the common area? 50%. See, the total is 4 centimeter, for example. This is 6 centimeter. Now, common area is only this. 2 centimeter is the common area. Both colors are. Now, instead of that, if I move my this plate like this, common area becomes less. Okay. Instead of that, if I move the plate like aligned together, common area is 10%. That means I can move the second plate, P2. Correct? P2 can be moved up. P1 is fixed. It will not move. P2 alone I am moving. By that I am varying area. Common area varying. Instead of that, I can vary up and down also this plate. I can align like this. Now I can move like this. I can move like this. Okay. So if I move totally, common area will move. both way I can change the capacitance. So other one is changing the distance D. That means this plate is fixed. P1 is fixed, it will not move. P2 I am moving in this direction. Okay, Z direction. So the D varies. So C can be, that's what is shown here. Another one thing what we can do is, if there are two plates, this is one plate P1, this is my P2, this is my, I told you, the two plates are conducting, but in between there's air. In this case, what is there in this case? The first case, here air is there. If it is an atmosphere, if I go to this one, it is a free space. Okay, instead of that, I can insert a dielectric non-conducting material. Correct? If I insert a non-conducting, same, the thickness is D. The thickness of this plate, the non-conducting material is D, which is pushed inside the two plates. Then what happens, as I push this, here it is air is there, and here I have a non-conducting material. This also has dielectric constant. This material can be any non-conducting material, glass, right? Polystyrene, mica, paper. So you will see paper capacitor. That means the dielectric media separate in between field is the paper. Paper is non-conducting, it has a dielectric relative can be maybe 2.5. The exact number we'll see. I may be there, otherwise you can refer. Similarly, glass. If I say glass is non-conducting, is ER maybe 4. Correct? And for example, polystyrene. Polystyrene is related dielectric constant, for example, 3.5, the 4.0. And the now instead of free space, I am filling the place inside the, this one is with any other non-conducting material. That means in this formula, what I'm doing, I am changing the epsilon value, ER, they call ER. ER is changed. Actually, we are changing epsilon, dielectric constant of the capacitor, but that can be found using this. E naught is the free space dielectric constant, ER is the material. Glass of the multiply using you will get, you can get like this, you can use it, the capacitor for measuring displacement. Okay. Now, if the capacitor can be, the plate can move up and down, that is, this is the D variation, I am varying D, or I can vary epsilon, permittivity of material by inserting different material, or the plate is one plate is fixed, other plate is moving. That is A is change. A change in A. A changes, here D changes, or here epsilon is changing. So in this formula, any one of this is changing, automatically C will vary. Now, if I calibrate, what I do in Z direction, I am moving the distance D. D is initially, for example, 1 centimeter. 2 centimeter, then what will happen? Capacitance. Capacitance C equal to, initially the 1 centimeter was the distance between two plates in here. Then a capacitance value, for example, 10 microfarad. Now I increase it to 11. Correct? Then it becomes something. Then I increase to 12. It becomes something like this. Then this is called calibration curve. Using this curve, once in the calibration curve, we know the capacitance value for different value for the given capacitor. Then if I attach the moving plate of the capacitor to moving object, and I will get the capacitance value using a capacitance bridge, then I can say how much the plate has moved, whether X direction, Y direction, calibration. That's how it works. Any doubts in this? Okay, no problem. So how will you measure the capacitance? Capacitance can be measured using what you call as AC bridge. The AC bridge is shown here. This is the AC bridge. Next, when we talk about staying here, we can go into DC bridge or Wheatstone bridge. AC bridge consists of voltage source which provides AC voltage, AC excitation voltage. That means you give a AC waveform with amplitude, for example, 10 volts peak to peak and maybe 1 kilohertz frequency. AC means the voltage is varying like a sinusoidal form with an amplitude, peak amplitude with this one. So that is supplied to bridge. This is the bridge supply. Then bridge has 4 arms. You can see the bottom 2 arms are a fixed resistance, we call R, and one resistance. This is the capacitance sensor. Okay, this is the sensor in which the CX value is varying from some minimum value to maximum when the capacitance.
Sir?
Yes, please.
Sorry to disturb, sir. Sir, what is phi, sir? In the three images, A, B, C, you denoted, you have denoted. So in that, you have some on the top and bottom, you have shown phi, sir. What is that, sir?
Top and
So means both the top and bottom plates both are connected with one symbol phi. So with
this is not pi. No. That is connection. Sorry.
so that is,
Not fine.
That is connection. That is connection, not this one. Just a lead wire end. It's not
okay,
pi.
okay. Understood.
Oh, thank you. Okay. Now this is called a AC bridge. Take this important. This is very important. AC bridge consists of 4 arms. Bottom 2 arms are having a resistor. Both the resistors will be equal. Say I call this R1, this R2. R1 will be equal to R2. Okay. Then top left arm, correct? I say is called a CX. This is your capacitance sensor because this value is going to vary, correct? So CX is unknown capacitor whose value will change because of variation D, variation A, or variation in epsilon, correct? If it varies, this value will change. This is what you want to measure. That means this is output. This is V0, bridge output. Note down, this is called bridge output. The bridge output is nothing but I have two. There are totally 4 components. We can divide into 2 half. I call left half and right half of the bridge. Left half consists of CX capacitor and R resistance. I can R1 resistor. This I call R2. Now, if I apply a voltage, then there will be a voltage at this point, V1. Correct? The voltage drop. This is supply voltage. The voltage, because there's a current flow in this circuit, the left half. So I is going. There will be 2 volts. I saw VCX. That means voltage across this. I say this is called a VR voltage. Okay. Now, if so based on the voltage do drop, the V1 will vary. We will see that. Similarly,
Sir, I'm sorry, sir, but where is VR on just R1?
VR1 is nothing but R1. You are correct.
Okay.
Okay. VR1. We are going to find the formula, what it is. Okay. Then the other one is again the same voltage is applied across the right side bridge. So because there's a current flowing like this and ends. Okay. I can draw in different color. This is the supply voltage. I say V excitation voltage. This is AC voltage. Okay. I apply 10 volts. And because of that, there's one current flowing like this. I have divided into 2 parts. Similarly, same voltage is applied in the second one because I am applying same voltage. From here, there's a voltage current flowing and comes like this. This I call I2. This I call I1. Because I1, there are 2 voltages. I call VR1. This is R1, this is R2. And this is called VCX, the voltage across this capacitor. This voltage is called V1. V1 is same as VR1. That's correct, 10% correct. Similarly, when I see this one, I call V2. V2 is nothing but the voltage across VR2. VR2, that means voltage across this resistor is called a V2. Now, the output voltage is the difference between V0. We say bridge output. V0 equal to V1 minus V2. Okay. Now, I am showing in terms of the resistor capacitor directly. You can see this is easier. Here, when we have capacitor or resistor is there, they have what you call impedance. Okay, impedance is this I call Z1. This is Z3 already we have shown. This is Z4. This is Z2. Now I say this is V1. This is V2. Okay, this is nothing but CX capacitor, and this capacitor is called calibration capacitor. Note down. Okay, now when CX equal to CS, this is called standard capacitor, calibration capacitor. Both the values are equal, and R1 equal to R2. Okay, then the V1 and V2 will be equal. If R1 equal to R2 and CX is this one, both are equal. That means my capacitor sensor initially it has, for example, 10 microfarad. Before the original value, without plates are have separated by some distance, both the plate are aligned. That time it is there. Now, if the plate moves, we know that the Cx will vary. If Cx varies, this voltage will vary. V1 will increase or decrease. Correct? Now, before doing any experiment or before using the capacitive sensor, the Cx value should be equal to C1. That is called a balanced condition. Balanced condition. What will happen? Cx capacitor will be as Cs and R1 will be same as R2. Okay. Now, this we are talking in sort of resistance capacitor value. Generally, when we talk a AC bridge, we talk in terms of impedance. The capacitor impedance is represented Z1, and that is Cx capacitor. Cs capacitor is as Z3, and the resistance value is shown as R1 is shown. Okay, here we are giving number itself. So R2, this is called as R4. Here I talk to R1, R2 because we are talking in terms of Z1. When you talk about impedance, we have Z1, Z2, Z3, Z4. Now, in the balance condition, correct? In balance condition, that means bridge output will be 0. V1 will be equal to V2. This is V1, this is V2. V0 equal to V1 minus V2 equal to 0. Because both are equal. Okay. Now, if the capacitor varies, this V2 will increase, but this is V1. We are called V1. V2 will remain constant because this capacitor will not move. This capacitor will be moving. So that means by measuring the delta V is nothing but V1 minus V2. I can find out what is the capacitance value at given time. That's how the capacitance sensor can be used for measuring the capacitance. Okay. Now, this is the parallel plate capacitor. I told you this is a parallel plate capacitor. Both are, as I told you, I'm showing again. So, because my hands, I am showing this is both are parallel. So, you can consider the parallel plate capacitor. Instead of that, we can have the plate shape can be anything. It can be circular plate or cylindrical. So, we are talking cylindrical capacitance. For example, there are two cylinders having a different diameter. One is D1, other one is D2. The D2 is a bigger cylinder. Please note that the cylinder is hollow cylinder because this is the cylinder wall, correct? This is having some metal, conducting metal. This one, D1 is smaller, D2 is bigger. So the smaller cylinder is inside, but they should not touch. There's a gap between these two. That distance is this is D. Okay, if there are two, see, under the cylinder has same length. Correct? The length of the cylinder is, for example, capital L. Both the cylinder equal length when it is fully aligned. When the small cylinder fully inserted inside, in this condition, both cylinders have equal length. So then they're not touching with each other with a gap of D. Then we know that it forms a capacitor. They call cylindrical capacitor. Okay. So cylindrical capacitor, what is capacitance formula? Note down the formula. C equal to 2 into P into ER into E0 into L divided by log, natural log of D2 divided by D1, where D2 is called as the outer cylinder diameter, D1 is inner cylinder, but it is smaller. Length is the common area. Again, I told you, like capacitance is in this formula, it provides how much length of the inner cylinder is inside this one. So the common area. Now, the common area is cylindrical surface. You know, surface of the cylinder, there's a formula. A can be calculated because the both the cylinder equal length, and both cylinders are aligned together. The inner area you can find out. It has a length L and D is the diameter. Then you can find out what is the common area. Okay. So because of there's a capacitance. Now, if the inner cylinder is moved out, pulled out, then the cylinder comes outside. Inner cylinder comes outside. Now, the common, this length is nothing but common length. Like common area, common length inside because automatically this one. So that is because reduced because it has moved this much displacement. So now if I pull further, okay, if I pull my inner cylinder outside like this, the common length becomes 0. Correct? The cylinder's inner cylinder complete come out, there's no common length. Similar to common area, common length, automatically the capacitance will become 0. Correct? There's no, this value becomes 0, capacitance 0. Now, if I move inside, the capacitance increases. It goes something like this. Correct? It goes like something like this. Finally, it aligns. So, by moving the inner cylinder left or right, I can change the common length. Automatically, the capacitor value changes. So, this is cylindrical capacitor. The formula is here. You can note down. Okay? P is a constant. P is a constant. P is a constant. Once the constant is given, you know the ER, E naught, length, D1, D2 is known, then you can calculate. What is ER? Is here ER is nothing, epsilon R. That is what is shown as ER. Don't get confused. And E naught is nothing but epsilon naught. Epsilon naught equal to 8.85 into 10 power minus 12 farad per meter. That is the dielectric constant of free space. ER is the relative dielectric constant. Note down. Relative dielectric constant of the dielectric media. Now air is there. It is filled with air. Automatically the
Sir, I didn't understand what is the operator Ln, sir. Can you please explain?
which one?
There is an Ln. Is that
Natural law.
There is
It is
one.
natural law.
Okay,
Natural
okay.
law of this.
Okay.
Correct? D2 divided. Say for example, D2 equal 10, D1 equal to 5. Correct? You are getting 2. You take natural log of 2. That value you have to substitute. This is called natural log. Ln is not parameter, natural log of D2
Okay.
divided by D1. Okay. So P is a constant. Once it is given, then you can calculate the ER equal to relative permittivity. Relative permittivity. Note down. It is called permittivity. Okay. That is very fun. Different material. Instead of air, I can fill another cylindrical shape having thickness. Correct? It has a thickness of this one. It is in cylindrical shape. This is my another material. I'm inserting in between. Correct? In the gap. So that means I'm filling this gap. Sorry, this gap with another material having relative. For example, it can be a plastic material. Correct? So it may be polystyrene having thickness. This is D. Correct? I'm inserting this additional one. I'm replacing air with this. In that case, then I have to replace this will be 2.2. For example, polystyrene is 2.2. This is 8.85 into 10 power minus 12. So this length already you know. This you can compute. So automatic capacitance. This is called as cylindrical capacitance. Note on the formula. In the exam, you can expect some problems. How it works also. Okay. Other one is, for example, I want to measure, but see this using this, what you can measure? Linear displacement. Correct? Cylindrical capacitor can be used for linear displacement because I am moving the inner cylinder. This is the inner cylinder. I am moving left or right. That how much I move that can be measured. Okay. But that means nothing but length is correct. Common area is measuring. That means there's a moving object to which the inner cylinder is attached. I want to know how much the moving object. Correct. For example, in your machine, something is moving. I want to measure this one. What do you do? The moving object can be attached to the inner cylinder. When it moves, outer cylinder is fixed. Correct. It is not fixed. So automatically the length changes. I can measure linear displacement. Correct. Now, if I want to measure angle, can I use the capacitor for measuring angle? Yes, you can. So I have two plates, semicircular plates. This is my P1. This is my P2. P1, you can see that it is fixed, correct? This is fixed, it cannot rotate. And both are equal radius. R1, I say R2. R1 equal to R2. Okay, then I will say this is R, common radius. Same size and is a semicircular. And they attach to a common shaft. Okay. But this plate is fixed, it cannot rotate. If I rotate this shaft, this plate will rotate. This plate will rotate clockwise, anti-clockwise. So this we are giving. In that case, I can think like this. There are two plates, correct? With a distance. This is the distance D. This is D. Distance between D. In this formula, this is the D. R is the radius of this one. And this is the rotation angle. If I rotate, what happens? The common area will, that means theta is varying. I wanted to measure, for example, I have a servo motor. Correct? I have a servo motor, which is, you are giving a voltage. Correct? We are supplying a voltage. So this is rotating. I want to measure the theta. What I do? I take two semicircular plates and attach like this. This is my capacitive sensor to measure angle. So if this shaft rotates, this plate will rotate, the common area reduces. Now both are aligned, correct? Both are the semicircular, both are aligned together. Now if the shaft rotates clockwise, this plate will move like this. Let me clear it and show you. So this plate would have moved something like this. because this is moved by theta degree. That is theta equal 30 degree. You can rotate it. Now you can see the common area reduced. Initially full. So now if I rotate further 90 degree, this will come something like this. The plate will be like this. Correct? So the common area go on reducing as I rotate. So then the capacitance will change. So using this formula, you can find out what is capacitance, and the capacitance can be measured using this bridge. The bridge can be used for measuring capacitance. So what is the formula for angle measurement? That is proposed. This is input variable theta, the shaft rotation, which is nothing but the rotating object angle I want to measure. That was theta. If I vary, automatically varies. So the ER is given. They are relative permeability of the material. Now it is air. Correct? I can fill this area with a dielectric, same shape, a dielectric having thickness. So in that case, my ER will be different. Multiplied by E0. E0 value, note down, this is the value. Okay. Then if I vary the theta, and C will vary. So I can measure angle. You can use this part. Then third, any doubt in this?
Sir, this angular rotation, which application we are using it, sir, currently?
Any shaft rotation. For example, you want to measure in your machine, you are controlling a motor, servo motor. For example, some spindle is rotated. Now, it is generally not used for measuring rotation speed. It is measuring angle. Wherever you want to measure angle, as I told you, motor control. For example, robots, I want to control joint angle. Correct? In robot, because we are using this kind of sensor in robot. This is my joint. The joint is attached with the motor. Okay, if motor rotates, the joint rotates. The rotation will not be 360 because this will come and hit. Generally, in robot, the theta, I say this is theta 1. It will vary from 0 to 180 degree or to 270 degree, not more than that. Any motor. So I want to measure how many degrees the joint has rotated. That means I want to control this motor. Angle measurement, for example, joint angle measurement. This is one example. Wherever you want to measure angle, which vary from 0 to something, you can use the capacitive sensor, non-contact. Okay.
Okay, sir. Okay, sir.
Okay.
Sir, I have a query, sir. I'm sorry.
Yes, please,
Can I
please.
ask?
Definitely.
Sir, in this angular rotation, like what I meant to say is picture, when the both semicircular plate are like
No.
perfectly.
No. This is attached.
I got the point, sir. I got the point. My question is like that is when the angle between this relative angle between these two plates are 0, okay, and suppose this is filled with air, there is no dielectric material between these two.
Yeah, the ER will be 1. You can say
1. Yes. Okay.
1.0015. You can take is 1.
Perfect, sir. Now suppose the angle is 30 degree.
Okay.
Suppose for time being. Then ER will be having some value and E0 will have some value. Right?
No, air only is there. No, see, common area only you are changing.
No. I'm suppose I have a like that dielectric material between that completely with the same shape. Suppose that ER value is 2 for that. Okay, for time being. Now when it is rotated by 30 degree or I would say like half the way of the angle between these two. Okay. Then what will the value of ER and epsilon epsilon 0?
No. Between the common area only you have to see. Other one is away. No. See, suppose if it comes like this.
Yes.
Correct. This area, it is not in the common area.
So ER will remain same.
Only, ER will remain same as the material what you are you another disk you have put. No, that way is going to remain. This is that because it's not in common area. So it is not going to have any effect.
Agreed, sir. So basically, R square and D both are not the function of area at the moment. Now, so that means this capacitance will not change in that sense. Because what I'm telling, sir, suppose theta is 30 for timing I'm telling, or halfway. R value is not changing because the radius remains constant.
Yes, D remains constant.
This remains constant. So even if I change the angle, the capacitance value will remain same exactly.
Yeah, but I got what you are saying. If I use another material having different dielectric constant ER, correct?
Right,
in
sir.
this case, air means is okay. This we are talking considering only air right now.
Right, sir.
If you use another material, formula will change.
And suppose air, if it is filled with air only, sir, suppose for time being, even if I change the angle, the capacitance from this formula should not change because R is a constant term, D is constant, epsilon is constant. Theta
Theta is varying, no? Theta
Okay.
represents the area, common area.
Okay, noted. Got it,
Okay.
sir. Fine.
Okay.
Thank you. Thank you.
Okay. Now,
Sir, one question from my side, sir, with regards to Angular thing. Does it have any industrial applications, or is it only at a small
no, a
scale?
lot of industrial application. Well, see, as I told, robotics is used. In my robot, I'm using the sensor, angle control, giant angle.
But
Correct?
then typically they will prefer servo kind of a thing, sir. Like
No, servo motor, for inside servo motor, we are going to, when you talk about motor, I will tell you, inside servo motor, you need angle sensor, feedback sensor.
yes.
Actually, servo motor consists of three parts. One DC motor, correct? The shaft. In the shaft is coming out. The other side of DC motor, you have angle sensor. How many
Okay.
degrees the motor? And this will be supplied with the voltage by a controller. Okay, this is controller. It measured, and you are going to say theta set point. I say 30 degree. And this sensor gives theta measured. What is current motor? So the difference theta error will be theta set point minus theta m. Correct? This error will be used to control the voltage. Voltage will be controlled based on the error. So you need a sensor inside this one. There they are using this capacitive sensor. You can use many type of angle sensor. Capacitive sensor can be used.
Okay.
Okay. Now the third type of the possibility I told you, change in dielectric constant. Correct. You know the C equal to epsilon minus divide L into W divided by D. Here I have two parallel plates. Correct. The total length is capital L. They divide into two half for understanding purpose. First half, correct. This length is called L1. The second half is called L2. The total length is capital L. Okay. In which, as I told you anything, this half here is filled with air. Here I have a dielectric media. That's what I already wrote. There's no need to write. Correct. So this is the half of the two parallel plates separated by a distance D. D is constant, correct? And the total length is divided in two parts. Understand purpose, the half of the parallel plate is filled with air. The related I call it 1.001. Correct? It is 0.01 or 0.015, something. You can take it 1. But the remaining half I filled with another dielectric, which is ER equal to 2. It can be, for example, paper, anything. Exactly, I don't know. Half of this one is filled with one dielectric constant, other one is filled with air. So what is the capacitance value? Now the capacitance of the total capacitor is nothing but C equal to epsilon multiplied by E0 multiplied by L1 into W. Correct? It is a parallel plate capacitor. That means there are two plates, something like this. Correct? Both plates. So the area of the half, correct? That is nothing but this. I can say capital A1. A1 half for this plate capacitor. Remaining half is same. This is A2. A2 is this. L2, this length multiplied by width. This is W. So this is area 2. This is area 1. D is going to remain constant. But only thing is half of the D is filled with air and half of the length, this one remaining there. In that case, this is my formula. Okay. So we can write this formula. You got it? Any doubt? So now.
Sir, I was trying to ask this only. So I think I've got this clarification now. Thank you.
Yeah. Now, if I attach.
Sir, but then I am so sorry for interrupting.
Yeah, no. Don't say sorry. Why? You are a student. I am here to help.
Okay, thank you, sir. Then we should not represent in the first equation, sir, right below the title. Then we should not call the second part as E epsilon R epsilon naught, right? One of them should change to epsilon 2 or epsilon M or
yeah,
something.
that's what I'm telling. This
Okay.
you substitute with 1.0015 for R. This you will substitute with 2.
Okay, so it is okay that we represent it with the same unit or same nomen.
Yeah, this will be multiplied by 8.815. And E0 is fixed into 10 power minus 12. Both equation 8.85 to E power 10 power minus 12. And your length this length L1 no. Yeah, similarly L2 W, the plate is a correct. Sorry, the plate is like this. This is divided into this. So you know the W. This is width. Correct? So automatically fill that, you will get the capacitance. Now it is 50%. So 50% of this is filled with this dielectric material, new dielectric, which has a 2, 50% filled with air, 1. Now, if I attach a moving object, I have some capacity. If I fill all this thing, I get it, say 100 nanofarad is coming, for example, at this kind. Now, if I attach this one, the moving object is pushing itself. Now it has come like this. Now what happened? My L2 can become bigger. If I say that this is 50 mm, this is also 50 mm originally, right? Now it become 25 mm. This will become 25 mm. This will become 75 mm. So the L2 becomes 75 mm. This will become 25 mm. So automatically I get a new capacitance value. So the change in capacitance C1 minus C2. C1 is originally is a delta C. The delta C only represents the movement of this object. As it moves, the delta C will increase or decrease. So not only formula, correct? So now we know the thickness is known. This can be written like this, correct? And when dielectric constant moved from a distance, after that I moved from new distance. This is what I'm saying. Now I inserted like this. This is my X distance. From originally it was 50%, now it has moved. In that case, when I move by this one, my formula changes. C equal to original C plus delta C. What is delta C? This C. Because of this further inserted, here it is reduced. That is change in distance. So can be written, take this formula. This is the derivative, this one, how we arrive. Now, if I move this object from any position, for example, initially, it was like this, whole thing was lying outside. This is my capacitor, 2 plates. This is ER equal to 2. Here ER equal to 1.0. I take 1 for understanding. This one. As I push inside, I can use this formula. Correct? I can use the formula from this. So this is attached to moving object. So this material is pushed inside little by little. Correct? Then I can measure. This is what? This is called a change in variation of dielectric constant. Correct? Capacitance, there are 3 parameters I can vary. I will go back. Very simple. C equal to, here also, C equal to epsilon A D. That's what I showed. The first figure A shows change in dielectric constant. The ER is varying. That's what we saw right now. Other one is, this is D is changing. Denominator changing, remaining are constant. In this, the common area is changing. That's what we talked all these things. Cylindrical capacitance, if I move left or right, the common length changes, automatically A changes. Literally, what it means is A is changing. Correct? So now I can move linear displacement. This is for angle displacement, angular measurement, linear displacement. And again, the third one also for linear displacement only. I am moving the dielectric media. Both the common area remains same, but both the parallel match, and this is how it works. Any doubt?
Sir, here we are considering L1 plus ER into L2 is very small and we are putting a 0 to derive delta C. How do we?
Which one?
At the end, delta C, we have kept epsilon R W into ER minus 1. Subtracted with, okay, sir. Right.
Okay. So I stop here. Tomorrow we will have the next sensor, inductive type sensors. What we are going to, how the inductor can be used for measuring inductive sensor, measuring RPM, or how it works. Then we'll talk about LVDT. Tomorrow we'll talk about LVDT. Okay.
Sir, ER for R is always 1.
Which one?
ER for R is always 1.
No. It changes depending upon moisture, dust, composition, dry air. For dry air, it is 1.0015 if I am correct. ER for dry air. If dust adds, because dust particles have different material, no, it can be wood particles or something, soil, floating soil, or for your soot particles. We talk dry air, pure dry air. which consists of only 77%, no water vapor, no any other dust particle, and dry condition.
Can you go back to the equation for that was explained again?
Here.
So here you are considering ERS1 to derive this equation. This C equation, when we are formulating C, we are ignoring epsilon R. I mean, in the first region, we are considering epsilon R as 1, and then we have derived this equation, right? So our assumption is YR with ER equal to 1.
Yeah, the ER equal to 1, close to free space.
Okay.
Okay, I stop here. Tomorrow, your exam is on Sunday. That will consider tomorrow portion also. From day 1 to up to tomorrow. Don't miss class tomorrow also.
Sir, Sir?
Yeah.
Sir, just now we received a mail that tomorrow IIT is closed. So we can have the class now, sir, even though it is a
No, I will continue.
Okay, thank you, sir.
Okay, because
One doubt, sir.
yeah. I am not able to hear you a little bit clear.
For ferrous to non-ferrous metal, whether ER will increase or decrease, sir?
Ferrous to non, see, metal are conducting, no?
Ferrous to non-ferrous material, like for metal to non-metal, if we say from metal to non-metal. So
see, all material has ER. Okay. Metals are conducting material. Their ER will be less compared to non-conducting metals.
Okay.
Generally, because you cannot use conducting material. If you use conducting, it will touch both the plates. That is very important. Please note that both the plates should not be touched. Suppose if I use a conducting material, sorry. Okay. Now, if it touches the correct dielectric material touches, capacitor itself not there.
Okay, sir.
Two parallel plates separated by a non-conducting material. The dielectric media should be non-conducting. The D, which is filling between the two plates, should be a non-conducting, not conducting material.
Understood.
Okay. Thank you.
Okay. Thank you, sir.
Okay. See you tomorrow, 5 o'clock. Class is there. Very important. Class. Don't miss it. For your exam, that is also important. I gave the clue because Roshan was asking for 2 days. So tomorrow class is also very, very important class. That is one of the clue.
Sir, I will ask tomorrow also, sir. Let me give another try.
Yeah, I already gave the clue, no? Today class is very important. Tomorrow class is very important. That's what that means. You should understand. I given open this one.
Sure, sir.
Clue.
Sure. Thank you, sir.
Okay. Thank you. See you tomorrow, 5 o'clock.
Thank you, sir.
We will see inductive sensor.
Thank you, sir.
Okay. Bye.
Thank you, sir.
Give your attendance before leaving. Chat message.
Sure, sir. Thank you, sir.
Thank you. Take care.